Just wanted to make sure. Okay. So as it says up there, the original idea of this talk was strategies for quicksort, and the reason for that is I became interested in quicksort recently because of a leak code question I did, and quicksort was something that I studied during my algorithms class, but we covered it pretty quickly, and it was kind of towards the end of the semester, so we didn't. To be honest, I didn't learn too much about it back then. But I did this question on leak code, and it kind of fascinated me. Especially, I learned a lot about quicksort, and in particular, people were talking in the comments about how to make it run quickly, because people were saying they found the solution, but it was running too slow for them. And so that kind of interested me. This talk did kind of turn out to be more about how quicksort works and not so much about the strategies. I will talk about the strategies at the end, but I don't know how many people here know about quicksort, but it's a pretty cool thing, or about sorting algorithms in general. But it's not really a Python specific thing. Of course, you could do it in any programming language, including Python. But in any case, quicksort. So what is quicksort? It's kind of like merge sort, if you're familiar with merge sort, and that is a divide and conquer sorting algorithm. But as opposed, how it differs from merge sort is the work for it is done in the divide step, or merge sort, all the work is done in that merging. So how it works is each iteration of the algorithm is going to choose what is called a pivot, which is why I have raw saying pivot there. And then it's going to sort the array such that all the items that are smaller than the pivot are going to be on the left side, and all the items that are larger are going to be on the right side, which is a pretty interesting way to do it. And then it's going to continually divide that until there's only one item left in the array, in which case, of course, one item is already sorted. Okay, so now the choice of pivot is extremely important in quicksort. And if you choose the pivot incorrectly, you are going to have a very bad time. Your running time will be O(n) squared, which is essentially the same as insertion sort. It's terrible. But if you make good choices, your running time will be O of n log of n, which is as good as merge sort. So if we look at the pseudocode for quicksort, what we're going to see here is we're going to take in the array, which is A, and then we're going to take in the beginning position and the end position, which is L and right, respectively. And then we're going to find that pivot, which is in line 3 there. And then we're going to divide it again in lines 4 and 5. So 4 is going to be the array to the left, and 5 is going to be the array to the right. And it's going to keep on doing this until it has just size 1. Okay, now if we look at how it's getting that pivot in that partition, what it's doing is, in this particular way I have it done here, which is the way you see it done often, is it's just taking that pivot, which is line 8, and it's just taking the most right side element, the one all the way over on the right hand side, and it's saying that's the pivot. And then it's going to take 2 pointers, I and J, and it's going to loop through all items in the array except for the pivot item, and assuming that the element that we're looking at is smaller than our pivot, then we're going to increase I, and we're going to swap I and J. And you're going to see how this works here in a second. And so what that means is we're only increasing I if the element we're looking at is smaller than our pivot. Okay. Then we're at the very end, we're going to take, how you end this is I is going to be at the item right before our pivot element. So in the last step, we're going to increase I once again, and we're going to swap the rightmost element, which is our pivot, and that element that's going to be right before pivot. And it's all going to make much more sense here once we see how this works. And then we're going to return that pivot. So this is showing how it works, and this is directly out of a textbook. It's called Introduction to Algorithms, and it's showing how this partitioning is working here. So our pivot in this case is going to be for that item all the way over on the right hand side, and I is actually off on the left hand side, off of the array, and J is element number 2. Ignore the P. I don't know why P is confusing, so just ignore that P. But what we're paying attention to is I and J. So what it's doing here is it's saying, is 2 less than 4? It is. So it's going to increase I, and then it's going to exchange that I and the J. So 2 gets swapped with itself. Then it's going to increase J. 8 is bigger than 4. 7 is bigger than 4. So J keeps increasing until it gets to 1. 1 is less than 4. So it's going to increase that I to where 8 is, and it's going to swap that 1 and that 8. Okay, so now we're at step number 5. And then it's going to increase that J again. 3 is less than 4. It does the same thing. It swaps 3 and 7. Then it keeps increasing J until we get to the last item. And then what it's going to do at the last step, it's going to increase that I once again in step 9. It's increasing that I once again and swapping the 8 and the 4. So this is very important. What it's doing here in that very last step is 4 was our pivot. And it's taking that pivot and putting it into where the sorted position in the array. So we know the 4 is already sorted. That's the position it's going to be in. And the next step would be, of course, to take those first 3 elements, 2, 1, and 3, and do the same thing to that one, and then take 7 through 8 and do the same thing to that one. You can keep doing that until the entire array is sorted. So why is quicksort good? Why would we use it instead of merge sort or instead of heap sort? As I mentioned before, in our best case scenario, quicksort runs of O n log n, which is the same as merge sort, the same as heap sort. So why would we ever do it? Why not just use one of those? And the answer is, first of all, quicksort runs in place, so it doesn't use any extra memory. As we saw, it's just swapping those elements. So it's good if your memory constraint is very good. Also, average case, which is a case you're going to be having almost every single time, unless you make bad decisions, is going to be just as good as merge sort. And also, and this is why I became interested in it, quicksort could be modified to do other things, which is what I saw in that leak code question. So in that leak code question, what they wanted me to do is to say what the kth highest element is. So they might say, what's the 3rd highest element, or what's the 5th highest element, which is not that easy to do. One way of doing it would be to sort all of the elements and then just say go to the kth position and pick that one. But instead of doing that, you can use quicksort to do this, and it's actually a different algorithm which is called quick select. I'm not really going to talk about it too much, except for what I just mentioned. I would encourage you to get on LeetCode and take a look at that problem, because it is pretty cool. But when do you not use quicksort? And the times when you don't want to use quicksort, and most importantly, is if you have a sorted or almost sorted array. If you use quicksort on an almost sorted array or a sorted array, you're going to be running an O of n squared time. And what I have there is an array that's sorted in reverse order, 5, 4, 3, 2, 1. And if you take a look at it, what we see is, assuming we use the method that I outlined before, our pivot's going to be 1, and it's going to go through all the elements, and it's going to swap 1 and 5, because all of the elements, 5, 4, 3, 2, are all bigger than 1. And then what it's going to do is, at that point, 1 was our pivot. So it's going to take your everything to the left, which is nothing, 0 elements, and sort that. There's nothing to sort. And then it's going to sort everything on the right side, which is 4, 3, 2, 5, which is only 1 item less than we have already sorted. That's the opposite of what we want to do. What we're aiming to do is to divide our array evenly. So the next iteration, you're going to be doing the same thing. You're going to be have 3 elements, and then you're going to have 2 elements and 1 element. And if we go through all this, that tree over there is essentially telling you is you're doing n squared work, which is bad. But this is what we're shooting for. We're shooting to, and this is, if you're familiar with merge sort, this looks exactly like merge sort does. We're dividing the array evenly each time, and the height of our tree is going to be log n. At each step, we're doing n work, so we're doing n log n times. So you might ask at this point, assuming that we were able to partition our array evenly each time. If we were magically able to do that, we would be doing this, but it's very unlikely we're going to be doing that. And so, is it really as good as log n? And the answer is yes, because even if we don't pick that median element every single time, it's going to all even out at the end. So I don't know if that makes sense. Hopefully it does. But in any case, how do we choose a better solution than just picking that right side element? What's a better solution than that? We can actually improve that. And there's 2 main ways of doing that. And that is to use a random element. In other words, instead of just saying the most right side element or the most left side element or whatever element you want to do, choose a random element. You have your left and you have your right, and choose a random element from there, which is what this pseudocode is doing. It's instead of calling quicksort, it's calling this random pivot, which is just getting a pivot, and then from there you're calling partition. And so that would be one way of handling this. The other and best solution is to do what they call a median pivot, and that is taking randomly pulling out a certain set of elements. In this example, I'm taking out 3 elements, and I'm saying, what's the median? So I take out 25, negative 15, and 14. 14 is your median, and that's going to be your pivot. All right. If you do this, it's going to, this is going to give you the best results. You do have to be careful because, of course, doing this is going to add to your runtime. So again, if you're using quicksort, you really want to be careful when you're using it and how you're using it. But it is really supposed to be the fastest sorting algorithm. And I put some resources here that are good resources for quicksort, especially the first one, which is the textbook that I took a lot of the information for this out of. And the fourth one, which is a very cool YouTube channel, back-to-back SWE. So he has a video on quicksort. So anyways, that is my talk.
Awesome. Thanks so much, Eric.
Yeah.
Any questions for Eric? And you can just unmute yourself and shout it out.
No questions, I guess.
Doesn't seem like there's any questions.
Okay.
It's been a fantastic explanation of quicksort. You know, I think this is great. I love that you talked about the, you know, sort of the limitations of it and when to use it, when not. Do you have any sort of like, I know you said it was from the leak code, but is there like a code base or anything that you want to promote? Usually I do like a today I learned on Twitter of these when we link up to them. So
there's nothing in particular, but there's a lot of implementations of quicksort out there. A DuckDuckGo search or Google search, whatever you use, will yield many results, and it's not that hard to implement. As far as the leak code problem, I don't remember what it was called. Unfortunately, I probably should have looked it up before I got on here. But if you search for quicksort or quick select on leak code, I'm sure it'll come up. There's actually a few problems about it, but the bottom line is as I said. So the problem is not really quicksort. It's a modification of quicksort, which is called quick select. And what that does is it takes quicksort and it combines it with binary search. So if you're familiar with binary search, you know what that is. And essentially, so what you're doing, as I said, the problem they wanted me to solve was to say that the kth highest element. So if it's the fourth highest element, for example, what you're going to do is you're going to do the first iteration of your quick sort, and then you can say, well, is the item that I'm looking at, the pivot, is it higher or lower than the element I want? So if it's higher, you're gonna go to the right. You're gonna discard whichever one is not relevant, and you're gonna go to the other one, which is just like binary search. And it actually results in being able to find your element and excuse me, O of n time. So, anyways, your question was really about code bases. So the answer is there's a lot of easily available code out there for quicksort and quick select.
All right, fantastic. Any other
Can
questions?
I actually,
Go ahead.
sorry. Yes, sorry, kind of adjacent to that, do I understand correctly that practically speaking, you would probably never do like implement it yourself in Python?
Yeah, that's an excellent point. Yes, of course, because sort is already built in to Python and most languages, so you're not really going to be implementing it yourself. But I believe it's still extremely important to know this this information. In fact, in my research, what I found out, and I didn't realize this, is a lot of languages, when they implement these sorting algorithms, it's not just one algorithm. So you can't say like, what does sort in Python? Does it use quicksort, or does it use merge sort, or what does it use? It might be using a combination. So it's going to look at the whatever you're passing in. It's going to say, well, I should use merge sort on this, or I should use heap sort on this, because that's what it's best to use.
Kind of on top of that, because Python is not typically, statically typed, it would be definitely faster to do that in like C and wrap around it.
Right. Yeah, well, as I said, if you're in Python and you're actually looking to sort, your best bet is just to use what they have, what's already built in. In that leak code question that I came across, that was a special scenario that you're probably not going to come across in real life. But as I said, I mean, to me, it's extremely important to know that stuff, anyways.
Yeah, it's kind of like soccer drills, right? Like the drills aren't the game, but
yeah,
the purpose of some of these exercises is to understand the mechanics and build muscle memory.
Exactly.
Yep. Cool. Thank you so much for sharing, Eric. I'm gonna
thank you for letting me.
Yeah, absolutely. I'm gonna spotlight you, Niels, next. Are you ready to go?
Yeah. Thanks, Lauren.
Oh, I have to remove the other spotlight. Look at this. Zoom's fancy. There's double spotlights now. All right, ready when you are.
Thanks. Hi, everyone. I'm Niels. And today I just wanted to share a library that I've been using for many years now. It's called Tools. And I'm not sure who's familiar with this. It's written, I think it was authored by Matthew Rockland, who is also the author of Dask. So I think this is one of the earlier libraries that he built. But if anyone's into functional programming and like functional tools in Python, this might be of interest to you. Yeah, the documentation is, you can just Google it real quick. It's tools.readthedocs.io. But yeah, I think I'll actually stay under the 5-minute constraint here. So I guess I'll just showcase a few of the things that I use it for most often. So I'm like a data scientist, so I'm like in pandas land a lot. But when I do need to use more kind of fundamental data structures like lists and dicts and whatnot, I'll usually use these functions, just kind of like a grab bag of tools that kind of helps me in certain cases when I feel like it. So here's group by, tools.group by. It's unlike the itertools implementation, which cares about the order of the inputs. So here it's creating a new group each time the input changes, depending on the the key function, which I'm just using the default here. The tools group by will just kind of group by a function that you give it. So it'll first apply the function to each value in the iterable, in this case, the length of the strings. And then that will be the group key on which it aggregates the values of the iterable. You can also give it the key in a list of dicts. So in this case, it will group by the whatever value is in the key. In this case, is just 1. So I found that pretty nifty in certain cases. There's a pipe function. I know there are other libraries that do this, but it's offered here. So the first argument is data you want to transform, and then the rest of the arguments are just functions. In this case, that just take single arguments. So it's just doubling 3, turning it into a string, copying it 10 times, and then applying tuple to it to produce a tuple containing 10 sixes, which are actually strings. There's a toy example, but if you have long pipelines, I kind of like architecting my code in this fashion so that it's, I find it to be, kind of nice to just see data being transformed in this way. Partition is nice if you do kind of machine learning stuff. This is really for the lazy because you can probably implement this pretty easily with just plain Python. But if you want to batch some data, you can use just this partition function, or partition all if you want to include batches of all the data and not just batches that are divisible by the first argument. So here, partition is just batching the data in groups of 3, and then it's dropping the last batch. But partition all will actually preserve the last batch that isn't divisible by that number. Finally, this is one I don't use that often, but it's, so basically tools is like iter tools and func tools with a lot more stuff in it. So this is useful for aggregation. So if you have a dictionary where values are iterables, you can apply functions. You can apply sum to bills, and it will apply that function to all the values in the dict. And so here you'll get the total values for each of Alice and Bob. If you want to make things faster, SciTools is the sibling package of this. It basically just implements everything in Python. So yeah, that's it. Just wanted to share.
Awesome. Any questions for Niels?
I have one. Is there any reason to use tools against SciTools? Like if I'm only starting with it?
I guess if you want everything in Python, like if for some reason your environment precludes like having another language for some reason, I don't know, like Python or C, then you would use tools. But I usually just install SciTools actually.
I think this is really cool. I had not heard of this library. I have heard of Matt Rocklin, but it's nice to be able to do more functional programming for sure.
Yeah, I found it to be a nice, it's like a gateway drug into functional programming, because you kind of like, there are a lot of stuff in there that's implemented in such a way that then if you go into like, I don't know, Haskell or OCaml, there are some like verb function names in there that are shared. And so you'll, kind of get some intuition as to what things are doing.
Yeah, I was just looking at the documentation on GitHub, and it says specifically, like, if you want to contribute, it's best if they, there's kind of a precedent in other functional languages. So that's cool. Any other questions? All right, thanks so much, Niels. Before I turn off the live stream, did anyone else want to speak tonight on the live stream that did not sign up on the spreadsheet? Okay, in that case, we'll close this down. Thanks for everyone who presented tonight, and we're going to go to our non-live stream version of this event.